The last video talked about things that are going on with climate change right now. And we talked about global temperatures. I left off with a little bit about the SOFAR channel and how we measure temperature, which takes us to changes that are happening in the ocean. And from here, we'll kind of go into predicted changes. So with the globe warming, we're also seeing sea surface temperature warm. I think you're fairly familiar with these types of pictures. We talked about them a lot when we talked about El Nino. Clearly, we have El Nino going on here. But you can also see that there's, in general, this picture is more red than blue, which shows you that it's warmer than it should, quote unquote, should be. Sea surface temperature has increased 0.6 degrees Celsius since 1970. It doesn't sound like a lot, but when you remember the high heat capacity of water, even a change that's only a little more than half a degree in 45 some odd years is quite a bit. So that's a lot. Also, related to the SOFAR channel and the ATOC experiment, deep ocean waters are beginning to show increase. It's not uniform. The deepest we found significant warming is at about 1 kilometer, right where that SOFAR channel is. But it's much faster than expected. Remember, they only really started looking for warmth in the deeper parts of the ocean in the 1990s. And just since then, they found it. Next slide. This is very related to the last chapter, changes in deep water circulation. So the North Atlantic needs cold, salty water to downwell, to sink, sort of, and this is a strange diagram, but it's in your book. So if this is the area off of Greenland, these surface waters come, they release a large amount of heat to the atmosphere. That's this right here. The water that remains is very cold. In addition, there's also fresh water coming in from here. Well, it's fresher than that water. That causes this water to sink. It becomes the North Atlantic deep water. And that is the engine. If you remember, it goes all the way back down and comes out and eventually becomes Antarctic bottom water and Antarctic intermediate water. So we need that in order to power the density-driven circulation or global Halian circulation, global thermohaline circulation. And one of the things that we know that's going on is in Greenland is one of the largest ice-based, land-based glaciers. And it's melting, and it's causing a large amount of fresh water to flood. So much fresh water that there's concern that the downwelling is not occurring at the same rate that it used to. This is kind of the big scary in that movie. Obviously, that's a movie and it's a fictionalized account. But they are seeing a freshening of the North Atlantic, which is a concern when it comes to global circulation. Ocean acidification, something near and dear to my heart. You should remember this equation when we put carbon dioxide in the water. We add the water, we get carbonic acid, which kind of goes back and forth between all this stuff. And how much it favors one product over another is going to be due to different factors in the ocean, like temperature and pressure and whatnot. But one thing that's inevitable, and this one bothers me, this is the only thing I don't like about it. This should be a single arrow that way. The more CO2 you put in, the more of these you get. This is the only part of that equation that is one direction. So make sure that you know that if you add more CO2, it is inevitable that you will get more of all these hydrogen ions. As I'm sure you super remember, or more likely vaguely remember, the more free hydrogen ions, like these guys, floating around in a liquid, the lower the pH. pH stands for the power of hydrogen. So the more hydrogens you have, the lower the pH and the more acidic it is. This diagram is in the book. As we have more CO2, the pH decreases. And this is stuff we're seeing already. And what happens is as you have more atmospheric carbon dioxide sinks into the water, which causes the ocean to become more acidic. And this is a problem for anything that's made out of calcium. Calcium likes to bond with carbonate, because that free carbonate will literally rip the calcium out of the calcifying organisms and soften their shells. And for many, it will kill them. These pictures are of some of those organisms. And hopefully these look familiar to you. These are coccolithophores. Coccolithophores were probably in bio, they called them the grass of the sea. Their primary productivity, primary producers, they lead to a lot of productivity of the ocean. There are estimates that coccolithophores and their immediate relatives produce something like 40% of the oxygen in the atmosphere. There's some debate about that number. But if these guys die, we're facing not just, you know, the loss of all the life that would eat them, but they're concerned about the amount of oxygen put into the atmosphere. This is a pteropod. Pteropod's like a little tiny snail. It's a plankton, and it is part of the food web, really important in some areas. Tends to be in colder water, and they will literally dissolve. They're tiny, tiny organisms. Sea urchins, the purple sea urchin, well-studied organism, and corals are all having problems already with marine with ocean acidification, and it's only going to get worse. OA stands for ocean acidification. In the North Pacific, which is where they've studied this the most, remember they put out all those buoys and there have been a lot of things going on. And they study atmospheric CO2 since the 50s in the North Pacific. So we know that since 1970, the pH has dropped by 0.04. Doesn't sound like a lot. But remember, it's a logarithmic scale. So every one change is like 10. So this is like a decent change. That's like 4% already. That's a good amount of change in the pH. There are some positive feedback loops that are concerning when it comes to OA, or ocean acidification. And one of them is, so whenever we have a feedback loop, we have the initial change, right? So we have a warmer atmosphere. When we have a warmer atmosphere, we have warmer water. Due to Hess's law, which I don't know if you remember again from chemistry, warm water holds less gases than cold water. So as we warm the oceans, that's his first positive feedback loop right here. As we warm the oceans, there will be less ability to hold CO2. So that's a concern, because if the CO2 isn't absorbed by the ocean, which it's basically been doing for us all along, that CO2 is going to sit in the atmosphere, and thus will continue to warm the planet, right? See how that was a positive feedback loop? Started with CO2 and warming and ends with more CO2 in the atmosphere and warming. Similar issue here as we get saturated. So as more and more CO2 enters the ocean because there's more in the atmosphere, it becomes saturated. No more CO2 can fit. And as that CO2 doesn't enter, it stays in the atmosphere. So you have more and more CO2 in the atmosphere. The third one's kind of the same one. Again, we were talking about warmth. One of the things warming can do, especially warmer surface waters, is slow downwelling. If there's less downwelling, the deep ocean no longer can become a reservoir for CO2, and it will just sit in the surface waters, become saturated, stay warm, and not allow more CO2 in the ocean. There is a point at which we are like this sort of equilibrium point where the ocean is going to stop absorbing all the CO2 that it does, which sounds good. Oh, there'll be less ocean acidification, but that will be a boomerang effect and have even more CO2 in the atmosphere. So it's kind of lose-lose. A predicted change, I want to talk about sea level rise as it's predicted. So we know it's occurring a little bit, depending on which measurement you use. It's between 20 and 40 or 50 centimeters. But the two main factors are the melting of glaciers. I highlighted glaciers. Please don't say sea ice. I know I put sea ice on here, but it's like sort of. I'll get to that in the second part. The main concern with sea level rise and melting is going to be of glaciers. Glaciers are ice that's on land. In general, sea ice is displacing more water than it would fill if it was melted. So like if you've ever seen that glass of water that has ice in it, you can have ice up above the rim. But even if it melts, it's not going to overflow because the ice is so, it expands, right? Water expands as it freezes. So when it melts, it condenses slightly. So there's that. Also related to glaciers are ice shelves. You'll see this when we watch this video about the Larsen B ice shelf, which I'm going to show you. And one of the issues is it's hard to predict how much sea level will rise. And this is something that we see a lot of wild predictions compared to some of the other ones. And we'll get into that when we do thermal expansion in a second. But there's kind of a cool video. I wonder if I'm going to be able to do this. Hold on. I'm going to pause. Okay, so I pulled up this video from the Jet Propulsion Lab at NASA. Hopefully you can hear it too.
We know that this ice shelf existed for at least 11,000 to 12,000 years. In 2002, two-thirds of it collapsed in less than 6 weeks. In the intervening period between 2002 and now, the remaining part of Larsen B has also been weakening very, very quickly. We expect it will not last for more than a few years to come. This will undoubtedly affect sea level rise by putting more ice into the ocean. Now we have this rare opportunity of this ice shelf destabilizing and eventually collapsing in front of our eyes. And that will give us incredibly valuable lessons that we could use to understand what might be happening elsewhere in the future. It is certainly a warning. The conclusion is inescapable.
Okay, so that was about the Larsen B ice shelf. The Larsen B ice shelf is one of the ice shelves that's on the peninsula on the western part of Antarctica, as you know. That's the area that's melting, and melting sounds nice and slow and constant, but what happens is you have these ice shelves, which are glaciers that extend out over the water. They're not floating in the water because they're fixed to the land, which is kind of an important issue. The Larsen B mostly let go. An area, the area was the size of Rhode Island, like 12,000 kilometers, but it was also 220 meters thick. So it was this giant piece of ice fell in the ocean. And then we kind of got to get to the next part, which is the thermal expansion. So ice ends up in the water and it melts. And there's a certain amount of just volume change because ice that was on land is now water in the ocean, and so be it. Thermal expansion is the notion that water expands as it warms. So we know that with fresh water, it reaches its maximum density at 4 degrees Celsius. Seawater reaches its maximum density like around 1 degree Celsius. So anything warmer than that, and it begins to expand. So as this water leaves the edges of the continent and becomes, I don't know, part of Antarctic bottom water, or eventually it will come up an upwell and it warms. When it warms, it expands. So one of the problems is we have wildly varying estimates on how much thermal expansion is going to have an effect. And this becomes an even bigger issue because we can estimate pretty good on the surface how much water is going to expand. But in the deep ocean, that water is subject to pressures that unlike anything we've seen at the surface. So it's hard to tell how much pressure versus temperature is going to cause water expansion. So thermal expansion has led to some wildly different predictions. So like in the IPCC in their most recent report, the relative concentration pathway with the most CO2, they have very conservative estimates. The IPCC is known for having really conservative estimates when it comes to sea level rise, and they have it as high as almost 0.8 of a meter by 2100. Other people, wild estimates have it at like 7 meters. I've seen many, though, especially for our part for the Atlantic, that puts it over a meter, which is of great concern. We are not at Sandy Hook 3 feet above sea level when you count waves, storm surge, and tides by any stretch of the imagination. So this is a concern. Other changes, we talked about sound transmission with the SOFAR channel. Related to that thing we talked about with the warm water, besides warm water holding less CO2, warm water also holds less dissolved oxygen. If you've ever gone out to a stream or a creek near your home, in the summer, sometimes you see the fish at the top gasping. That's happening in parts of the ocean, what we call marine dead zones, but there's one in the Gulf of Mexico that's very famous. But marine dead zones are actually expanding because as the water gets warmer, it holds less oxygen and you have less life in the area. Again, I mentioned the coccolithophores before. When you have this acidified seawater, it's going to change productivity because organisms that are the primary producers are very small. They usually have shells, and they're very susceptible to ocean acidification. And some of the research kids know this. Marine organisms are trying to adapt to temperature changes. This happens two ways. They shift their ranges more poleward. And if you could talk to Alex Sipis, he would tell you how the flounder are moving more northward. A lot of organisms that live on the continental shelves are actually trying to move deeper. Instead of just going northward, they're going deeper. That produces other issues, less availability for food, differences in oxygen and nutrients. So we're seeing a rapid change in evolution kind of going on right now. I'm going to stop right there.